So we're going to continue to get better with working with the sine and cosine function, and solving trigonometric equations is really what we're going to work on. Now, in this particular problem, they actually just ask you for a value, but I want to kind of approach this the way that's it's going to help you out moving forward. So the way to help you out moving forward is to recognize that you've got a couple squared terms. But when you have squared terms like that, it always comes back to the Pythagorean theorem. Now, there's a bunch of different versions of the Pythagorean theorem, and even though I've been teaching this class forever, I don't have them memorized. What I do when I need them is I kind of derive them. So which one should I derive? Well, that's actually kind of driven by what we have here. So let's look at cosecant squared minus cotangent squared, and think about cosecant and cotangent. In terms of sines and cosines, what's your cosecant function? Anyone?
1 over sine?
1 over sine. Thank you, Durade. 1 over sine. And someone else help me out for the cotangent.
Cosine over sine.
Cosine over sine. Nice. So what's happened is that our function here, excuse me, our identity here has been divided by a sine term. Not just any sine term, but sine squared. Sine squared, sine squared, sine squared. Now, if I divide everything by sine squared, what am I going to get? Well, the first term should be pretty simple, right? That's just going to be a 1. Plus, what term do I get here?
Cotangent squared?
Cotangent squared equals cosecant squared. Now that's pretty close to what I have here. What's the difference? Well, what I have here, I've got a cosecant squared minus cotangent squared. So what's the last thing I can do with this to try and get something like this?
Minus your cotangent squared.
Yeah. We're going to move that to the other side, so we're going to subtract cotangent squared from both sides, so that I get 1 equals cotangent squared of x minus cosecant squared of x. Well, that's kind of bizarre, that no matter what, when you take the cotangent squared and you subtract the cosecant squared, you're going to get 1. In particular, that's going to be true right here. That is going to equal 1. And that's it. That's your answer there.
Wouldn't it be cosecant squared minus cotangent squared?
Oh, you know what? I got them backwards, don't I? Did I copy it down right? Let me take a look here. Let's see. Cosecant. Oh, okay. All right. So that's fine too. We can work with that. Let me work backwards, or let me rework this. So this is cotangent squared minus cosecant squared. If I wanted to arrange things to get this, and I appreciate you saying something there, I just wasn't paying attention. If I wanted to get something like this, then I got to have, let's see. Wait a minute. Oh, I just copied it down wrong here, right? That's
Yeah.
Yeah, okay. So it's going to be 1 equals cosecant squared x minus cotangent squared x. You could have done it the other way. I could have moved this over here and then this over there. Then I would have got cotangent squared minus cosecant squared would have been -1 had I did it that way. But you're right. Now, the good news is I do have this part right. And we can take a quick look at a little visual of this as well, because it's kind of bizarre. If you look at the graph of the cosecant squared, it looks like this. And the graph of the cotangent squared looks like that. Notice that they're kind of stacked on top of another. They're always the same distance away from each other if you look vertically. And just to highlight that, let's graph y equals cosecant squared minus cotangent squared, and you always get 1. period. So that's kind of cool. That's our answer, 1. Comments or thoughts on that? Let's move to this next one here. Tangent of 1 equals, or excuse me, tangent of theta equals 1. And let's see. Let's maybe look at our unit circle here. If you pull out your unit circle, you'll want to find the places where the tangent is 1. Now you see the tangent is 1 in a couple of places. One of them is right here at 45 degrees. But the other one is down here at 225 degrees. Now I should probably be talking about this in terms of radians, because calculus is done in radians and I want to get you ready for calculus. So pi over 4 and 5 pi over 4. The thing about tangent that you need to keep in mind is that tangent is periodic with period pi. So if I move a distance of pi, so go from here to here, then I'm going to find the exact same place on the unit circle with a tangent. Well, not the exact same place in the unit circle, but I'm going to find the exact same value for the tangent, which is 1. So this keeps on going forever and ever, though. If I add another pi, get back here, tangent is still 1. And then I can keep going, add another pi. So what the solution is showing you is that pi does have that periodicity, and that you can keep on adding pi to your answer of pi over 4 to keep on getting as many solutions as you want. So that's what's going on there. The bottom line to keep in mind is that, let's see, period equals pi. There's going to be 2 functions where the period is equal to pi. That's going to be the tangent and what else?
Cotangent.
Thank you, cotangent. Tangent and the cotangent of x. For period equal to pi, there's sine of x, cosine of x, and the reciprocals have the same period. So there'd be cosecant of x and secant of x. Let's play around with the sine and cosine functions for a bit. Now, a lot of times when you work with these formulas, you get solutions to equations, but you don't want just one solution. You want to represent all solutions. Like here, this represents all the solutions to this equation. It's pi over 4 plus any integer multiple of pi. In this next one, we've got solutions of this form. There's 2 of them. Theta equals pi over 2 plus 2k pi, or, I'll do it in a different color here, theta equals 13 pi over 2 plus 2k pi. It says, which of the following is not a solution? So let's play around with that a little bit and see if we can't figure out which one of these is not a solution. And to do that, what we're really going to have to do is plug in some values of k to try and find, well, what angles are solutions? What's in that solution set? So let's work with theta equals pi over 2 plus 2k pi. I think it's worth a little bit of effort to clean this up and maybe write it with one fraction. Now let me show you how I'm going to do that. First of all, I'm going to factor out the pi from here and pi from here. So it's going to be 1/2 plus 2k times pi. And then I want to write this with a common denominator. But right now, there's no common denominator here. In fact, there's no denominator here at all. So I can think of this as 2 over 1. Well, what would a common denominator be for these two terms? No one? Common denominator between 1 and 2?
Number 2.
just 2, right?
Yes.
So we can get a common denominator if I multiply this by 2 over 2. Now, what does that give me in the numerator? Gives me a
Common denominator of 2.
yeah, 4k over 2, and you got that common denominator of 2. That's what I wanted. The reason I wanted that is I can bring that together as one fraction. It's going to be 1 plus 4k over 2 times pi. Those are going to be my solutions. Now, it took a little bit of work to get here, but if you're unclear about something, let me know. So let's take a look at our solutions then, or some solutions. And the solutions are going to be are going to be dependent on values of k. So probably want to start out by letting k equal 0. If I put in a k equals 0 there, what's that going to give me for theta? 4 times 0 plus 1 divided by 2.
1/2.
It's going to be 1/2. 1/2 times pi over 2, or pi over 1/2 times pi, or pi over 2. Cool. How about if k equals 1? Now what will I get here?
5 pi over 2.
5 pi over 2. Or you can think of it as 5/2 pi, and so on. You can get as many solutions as you want. Now that's half of your solution, or half of your solution set, I should say. It's coming from this. There was another one that was part of this as well. So let's take a look at that. Before I let you try the other part and write it as one fraction, are you okay with this part? Is there something I can clear up, because I want you to try it next? All right. So let's look at the other part then. The other part looks like this. 13 pi over 2 plus 2k pi over 2. So, okay, let's work with that. Theta equals 13 pi over 2 plus 2k pi. Let's see if we can't make something there work. Remember, start by factoring out the pi. And then get a common denominator. Okay, so kind of like the last one, 13 over 2 plus 2k over 1, all that times pi, we want to get a common denominator. The common denominator is going to be 2, so I'll multiply this by 2 over 2. That'll give me 13 over 2 plus 4k pi. It's going to be 4k over 2. The pi is going to be outside, like that. These now have a common denominator. So I can rewrite this as 13 plus 4k over 2 times pi. And kind of like the last one, I can now set up a table and find as many answers as I need. I'll plug in values of k, get out values of theta. So let's do 0, 1, and 2. At 0, you just get 13 over 2 times pi. How about at 1? What are you going to get there? 13 plus 4 is 17.
17 pi, or 17 over 2 pi.
17 over 2 pi, or 17 pi over 2. And let's do the last one. Last one should give me Anyone?
1 pi over 2.
Thank you. 21 pi over 2. If you look back then, I think the one that we miss is this one. 23 pi over 2 is not going to be a solution. We did see 17 pi over 2. That one was a solution. And look back, 5 pi over 2. 5 pi over 2 was a solution from the first part. It was a solution from the yellow part.
Oh, okay.
So if you look back to that yellow part, then yeah, there was the 5.
I thought they were separate equations for a second.
Okay, yeah. No, I just did them consecutively, that's all. So, all right, good deal, good deal. Now, you're not always going to be given that. You're going to have to kind of work with that yourself. So let's ease into something like that. Let's see. Let's see. We'll start with this one. 4 secant theta plus 1 equals 9. And we want solutions between 0 and 2 pi. So that's kind of a nice restriction there. It means we don't have to worry about like everything under the sun. 4 secant theta plus, what is it, 1 equals 9? Is that it? Yeah, 1 equals 9. I would start by isolating the trigonometric term here. So I'll subtract 1 from both sides and get 4 secant theta equals 9. Let's give, how about 8? Secant theta equals 2. Divide both sides by 4. And now it's up to you. But for myself, I'm much more comfortable working with sine and cosine than I am secant and cosecant, or tangent and cotangent for that matter. So I get 1 over cosine theta equals 2. And I guess I'll just do this in a nice formal way. Let's multiply both sides by cosine of theta to clear out the denominators. And that'll give me 1 on the left-hand side equals 2 cosine of theta. Almost done with the preliminary part. I'll finish up by dividing both sides by 2 and get 1/2 is cosine of theta. All right. Now this part's not too bad. You can do this a couple ways. You could look at your unit circle. You could use the inverse cosine, but it's probably not a bad idea to look at the inverse, as you look at the unit circle. So let's take a peek at that. So let's see. What we're looking for is places on the unit circle that have a cosine equal to 1/2. That's going to mean an x coordinate of 1/2. So where's that going to be?
Pi over 3 and pi over 3.
There we go. So there's 2 places. Pi over 3 right up here, and 5 pi over 3 down in the 4th quadrant. So down here. Awesome. And that's it. You're done. Pi over 3 and 5 pi over 3. So pi over 3 or 5 pi over 3. Now we're fortunate that we're just asked for those 2 because we're looking in the interval 0 to 2 pi. But if you weren't asked for just those 2, if you're asked for everything, then you could expand that and give everything this way. You could say pi over 3 plus 2k times pi. That is multiples of 2k times pi. Because if you add a multiple of 2 pi, you're really going to get back to the same spot. 5 pi over 3 plus 2k pi. Yay. So, we're good on that one?
Yeah.
this little extra part here
Um,
is a little challenging. Yes, please.
do you think you could explain a little bit on the 5 pi over 3? I'm looking at my unit circle and trying to understand how you got to that.
Sure.
Yeah,
Let's-
wouldn't that be negative 1/2?
Good question. Good question. Cosine is which coordinate on the unit circle?
X.
The x coordinate, right? So let me see if I can erase some of this stuff here and focus in on the x coordinate. All right, so I want an x coordinate of 1/2, right? So that's going to be right up here at pi over 3, right? And I can draw a straight line down to that other part of the unit circle that has an x coordinate of 1/2. And that is right here at 5 pi over 3. See how they both have x coordinates of 1/2?
Oh, I see it now. I was thinking more so like when you were doing the, like add another pi, because I was looking at,
Oh, okay.
what number is it? The 240 degrees.
Got it. Got it. But do you see that both of these have the same x coordinate of 1/2?
Yeah.
Okay, good, good. There was someone else that was a little unsure about this one. Are we good?
Yeah, I got it. Thank you.
Okay, thank you. All right, so let's move on then. Went back to, no, it's not what I wanted. Let's look at sine of 2 theta equals 1/2. Now, again, fortunately, we're just asked for the solutions in the interval 0 to 2 pi. So sine of theta, excuse me, sine of 2 theta equals negative 1/2. Ready, fire, aim. Right here. This is where we're going to start using our inverse trigonometric relations. So sine of 2 theta equals negative 1/2. What I'm going to do is I want to get at theta. I want to eventually solve for theta. So what I'll do is I'll take the sine inverse on both sides of this equation. Now, why the sine inverse? Because the sine and the sine inverse are going to cancel each other out. So if I do sine inverse here and sine inverse here, on the left-hand side, what will I be left with? What's going to be left on the left-hand side?
2 theta.
Thank you. Awesome. 2 theta. 2 theta. And on the right-hand side, we're looking for places where the sine is negative 1/2. The sine is which coordinate on the unit circle?
Y coordinate.
Y coordinate. Good. Thanks, Pat. So we're looking for places where the Y coordinate is negative 1/2. Let's go back to our unit circle. Even in an in-class, face-to-face class, I would let them use a copy of the unit circle that the students fill in themselves. It's really helpful. So I'm looking for places where the sine, the Y value is negative 1/2. Can anyone tell me where those are going to be?
7 pi over 6.
7 pi over 6. Thanks, Kirsten. That's one of them.
11 pi over 6.
And 11 pi over 6. So if we draw a little line here at negative 1/2, you see the two places where the sine is negative 1/2. So it's going to be 7 pi over 6 and 11 pi over 6. Both of them have a Y coordinate of negative 1/2. So let's write that down for ourselves. 2 theta could be pi over, so 7 pi over 6, leave a little space here, actually a generous amount of space, or 7 pi, or yeah, I already got that one. How about 11 pi over 6? Yeah. Bad day. 11 pi over 6. Right? Either of those work. But kind of building off our last problem, we're also going to add 2k pi. It's 2k pi. Ooh. So this has all been building up to this moment, being able to solve these types of equations. Are you okay with the two solutions we got? We got 7 pi over 6 and 11 pi over 6. Those are just the answers to the inverse sine of -1/2. And then we're adding these multiples of 2 pi. All right, so we're good up to here, yes?
Yes.
All right,
So really quick.
go ahead, Pat.
So we first solved for just between 0 and 2 pi, and then
Right.
we had the 2k pi for the
Yes.
for the rest of everything else. Okay.
Right, because this angle here, 2 theta, it could be, 7 pi over 6, or if you add, say, a multiple of 2 pi, a multiple of 2 pi is going to bring you right back to here. It's not going to look like 7 pi over 6 anymore, but it's going to bring you to the same angle, which will have the same y coordinate. And likewise over here, if I started out with, say, 11 pi over 6 and added a multiple of 2 pi, that would bring me all the way around back to here. And once again, I'm going to have the same y coordinate of -1/2.
Okay.
All right, good. Let's keep going then. So I'm going to divide both sides by 2 to finish solving this. Or instead of dividing by 2, maybe it'd be more efficient, a little bit easier to work with if I multiply by the reciprocal. What's the reciprocal there?
Half.
Yeah, 1/2. So I'll do 1/2 times everything. So I'm multiplying the whole equation by 1/2. On the left-hand side, I get theta. On the right-hand side, I get 7 pi over 12 plus k pi. And that's your general solution. I'll work with that a little bit and look back at it. I'll show you what it means graphically, but that's part of your general solution. There's another part up here. So let's finish solving that second part. And I'll do the same thing that I did before. I'll start out with a 2 theta equals 11 pi over 6 plus 2k pi. And once again, I'm going to multiply by the reciprocal here. 1/2. That's going to simplify to 11 pi over 6 plus k pi. If you play our game that we played earlier of getting common denominators, this would be 7 pi over 12 plus 12k pi over 12. So notice that they have common denominators. I just multiply this by 12 over 12. Or overall, factoring out the pi, you could write this as 7 plus 12k over 12 times pi. And sorry, I ran out of room there a little bit on that last pi, but there's a pi here. So let me just write it down below. 7 plus 12k over 12 times pi. That's your general solution, at least part of your general solution. Maybe you want to pause the video if you're watching this at home or something like that. Give yourself a chance to try this one. This one would turn out to be,
Sorry.
yeah, question.
Shouldn't that be theta equals 11 pi over 12 plus k pi?
Oh yeah, thank you. 12, thank you. Yep. So good thing you caught me before I asked or finished pausing on this. So this is going to turn out to be 11 plus 12k over 12 times pi. So these two are going to be your general solution here. Both of those. And you can get as many solutions as you want, starting with those two. If you made a little list, k, and then call it maybe theta 1 and theta 2, or whatever, 7 plus 12k over 12 times pi. And then the other one, 11 plus 12k over 12 times pi. You can do k equals 0, 1, and 2 to see some of the first few solutions. So at k equals 0, you're going to get 7/12 pi, or 11/12 pi. At k equal 1, you're going to get 19 over 12 times pi, or 23 over 12 times pi. And I'll finish up with k equals 2. 24 and 7 is going to be 31 over 12 times pi, and 35 over 12 times pi. So those would be the first few solutions for something like that. Let's see if the graph kind of tells us the same story. So we want to see where sine of 2 theta equals -1/2. So let's take a look at the graph. Now, initially, a lot of problems, you're just worried about a solution in the interval 0 to 2 pi. And if that was the case, you could look at the graph of y equals sine of x and say, oh, well, there's two solutions, right? 7 pi over 6 and 11 pi over 6. We found those solutions. That's great. But when you add in the graph of y equals sine of 2x, you realize that there's more than just those two solutions. So let me shut off this graph. In the interval 0 to 2 pi, there's a lot of solutions, right? There's actually 4 of them. There's one that we got, 7 pi over 12. Here's another one that we got, which was 11 pi over 12. Any guesses on that one? Yep, 19 pi over 12, 23 pi over 12. And that's just in the interval 0 to 2 pi. Now, if all you were looking for is the interval 0 to 2 pi, you'd be done. But I hope you realize and understand that there's a lot more solutions, right? In fact, we found some of them, 31 pi over 2, 35 pi over, not over 2, over 12, etc. There's an infinite number of solutions, which is why we have to write it like this. You don't have to write it exactly like that. It's just convenient in terms of grinding it out. Okay. There's a lot on that last one there. So I'll pause here for a second, see if you had any quick questions on that one. If not, there's one last example that I promised I'd do. All right. So the last example that I promised was kind of hinted at in the quiz video check, and that was cosine of theta equals negative 0.52. So cosine of theta equals negative 0.52. So what you're looking for here is a value of theta such that the x coordinate is going to be negative 0.52. So where's that going to be? Let's take a look at the graph. And I believe this is on your handout. Negative 0.52 is about here. And if you keep an eye on things, there's two angles you're going to be looking for, this light blue one and this purple one. So that light blue one is something that you can get from the inverse cosine. If you take the inverse cosine, theta is going to be the inverse cosine of negative 0.52. So let's do that on our calculators. Make sure you're in radian mode. Inverse cosine of negative 0.52. That's going to give me my first answer, about 2.91 or 2.117. So that's one way. Oops. So that's this way. But that angle that way should be the same as this distance this way, right? If I went the negative direction or the positive direction, I'm still moving that same angle. It's just that we don't typically think of angles this way because that's a negative angle. So how would you get the positive angle? Can anyone figure out how we get things this way? What would the measure be that way?
Is it 2 pi?
Well, it's not quite 2 pi. 2 pi would be all the way around, but I want to go all the way around and then back up a little bit. I want to
Or 2 pi negative
2 pi
Minus-
negative,
0.
Right, minus the same angle.
yeah, 2 pi minus that angle. Perfect.
Yeah.
So that's all you got to do is take our other angle is going to be 2 pi minus cosine inverse of negative 0.52. That's going to be your other angle. So call that theta 1, and that's going to be theta 2. Those are your two angles. You can check it for yourself. If I did 2 pi minus my previous answer, so second and then answer, that's going to give me another angle. If I was to take the cosine of that, I should get about 0.52. It might not be exact, but it should be close enough. There you go, negative 0.52. Okay, that'll do it. Let me pause things here.